Hello everyone! Today we're going to be talking about the math of the braking distance. So now we're going to start doing some calculations. So we've already talked about how speed is related to braking distance. We can actually formalize this a little bit. We can say that as velocity increases, the speed increases as a share of that velocity. So if you doubled your speed, then your braking distance would be 4 times greater. So this is one of the reasons that we have a speed limit in our school zones. So our school zones are 30 kilometers per hour compared to the normal speed of compared to 60 kilometers per hour on most of our roads. And so that essentially means that there is going to be that the braking distance should be about 1/4 normal in the school zone. Okay, so the speed is half, right? So this is 1/2 the speed, and so that means that we will get 1/4 the braking distance. So if it was going to take you 1 meter to stop, you'll be able to stop in 0.25 meters. Only 250 centimeters or something, or 25 centimeters. If it was going to take you 4 meters to stop, you'll be able to stop in 1 in a school zone, and that's really important when you have the risk of children running out in front of your car. So that's one of the reasons that those numbers are the way they are. Is that they did consider this idea that braking distance is proportional to the square of your speed. Now this is also going to be impacted by the frictional constant. This is the value that we discussed at a previous time. This is related to frictional coefficient, but it's a little different. It is a constant that accounts for the type of surface that we're talking about. So whether it is dry pavement or if it's ice, and how that surface interacts with a usual car or the material. So in this case, all of these constants have been calculated with respect to a rubber tire. So in dry pavement, the frictional constant is 0.06, wet concrete 0.1, snow or ice 0.15. Those are the three we're going to use regularly. As K goes up, then the braking distance is going to increase. So that's how they're kind of related. So the larger the frictional constant, the less friction there is. So it's a little bit of inverse to how some of our later equations in our physics, physics 30 or 40s is going to be. We'll talk about a different value called the frictional coefficient, which has a different relationship. But right now, this is good enough. The frictional constant is going to, as it increases, the amount of friction is decreasing between the surfaces. So that means that the distance is going to increase. So now we can add this into that proportionality we mentioned earlier, and we can say that the braking distance is equal to this frictional constant times the speed squared. And that creates an equation now, d equals kv squared. So for example, let's find the braking distance of a car driving on dry pavement. So that would be the 0.06 k at a speed of 50 kilometers per hour. So we got v, we have k, and now they want to find that d distance. So first we need to convert, because notice in the table that the value is in meters per second. So we have to convert that kilometers per hour into meters per second. This is okay the way that they've done it. I'm going to show you how I organize it. So I organize it this way. I always place my kilometers and per hour as a fraction. And this way, the kilometers that are on top here can be divided away by this proportional value here. There is 1,000 meters in 1 kilometer. There is 3,600 seconds in 1 hour, or 1 hour is made of 3,600 seconds, can be divided into 3,600 seconds. So we organize it this way, and now we can see that the hours is on the numerator versus the denominator that we started with. So those also cancel. This leaves only the meters and the seconds behind at the end. So when we multiply across this these set of fractions, we're going to have sort of 50 times 1,000. You can divide by 1 if you like. Times 1 divided by 3,600. Of course, this can be simplified to be 50 times 1,000 divided by 3,600. That will also work in your calculator, whichever way you're most comfortable with. And so that will be the 13.9 meters per second. So now that value is going to go in here, and we're going to square that. We're going to do the k times that v squared to give us a distance. Now, what if we were talking about, what if this was ice? How about ice and snow? What would happen then? So let's try this again. We're going to take the same v, 13.9 meters per second. We're going to square that, but now we're going to use the other value. So let's go back up. Ice, snow, and ice is 0.15. So 0.15. We're going to multiply those two to get our distance. So let's see what happens. 0.15 times 13.9 squared equals 28.98 meters. So that's quite a big difference, right? That's more than twice the distance for braking from the dry pavement. So think about that if you're driving in the winter and you don't have winter tires, you might be experiencing twice the braking distance or more, depending on how icy and how much ice and snow there is. Certainly, I've slid through the occasional intersection, or I remember one time I slid very slowly into a tree. There was no damage, but I did slide right across I was going very slowly down in a residential area, and then my car just kept sliding and sliding and sliding, and there's nothing I could do to stop it. Okay, so in the practice questions, we have a car traveling at 66 meters per second. So that's our V. On slippery concrete, I'm going to assume this means 0.10, the wet concrete. So that's going to be K equals 0.10. I'll be more clear in the questions that I ask what I mean by the coefficient and how much distance is needed to stop their car. So here we're going to do, again, D equals K times V squared. And we're going to say that the K is 0.10. And we're going to multiply that by the V, which is 66. And we're going to raise that to the power of 2. Push that into our calculator. 0.1 times 66 squared. And the value we get is 435.6 meters. And they say 1 decimal place, so we are only going to include that 6. 435.6 meters. So of course this is very, very fast. 66 meters per second is like 230 kilometers per hour. So it's like a race car or something. But that did save us a little bit of a job in converting. Okay, so let's look at the next one. The next one starts with kilometers per hour. So let's set that up. We need that we need to convert that to meters per second. So 90 kilometers per hour times the 1,000 meters in 1 kilometer multiplied by 1 hour, which can be divided into 3,600 seconds. And so the hours will cancel, the kilometers will cancel, and the value will be 90 times 1,000 divided by 3,600, 25. So this is going to be 25 meters per second. And so now we're going to insert that into a snowy conditions. So here the K is going to be equal to 0.15, just like it says in the table. And we're going to say that D is equal to 0.15 multiplied by 25 squared. And so that is going to be 0.15 multiplied by 25 to the power of 2. and that gives us 93.75. 93.75 says to 2 decimal places, so we'll keep both of those, and we'll call this meters. 93.75 meters. And that's how you do these questions. These are all pretty straightforward. There is a possible way we could play around with it, but where we could invert the question a little bit. We could say, let's try one last question. This will be a challenge question here. So it takes John 3 meters to stop his car on dry pavement. How fast was he going? He driving? Okay, so that's sort of that's an inversion of the questions we've been doing so far. So that's that might be a little bit challenging for us. So here we have the distance, and we have dry pavement, which we know is 0.06, so that's our k. And what we're missing is v. So when we think of our equation, d equals kv squared, we can invert this to be d over k, and if we take the square root, we'll be left with v. And you can just take my word for that. You don't have to do this. We could also imagine one other version of the equation. If we needed to solve for k, we would say that d is divided by v squared. Okay, so that's off to the side. We're not going to use that right now. So let's just put in our values. We're going to put a square root here. We're going to put the distance, 3 meters. We're going to divide that 3 meters by 0.06. And I'm guessing we're going to get a pretty small number here, but we'll see. So square root of 3 divided by 0.06 equals 7 meters per second. 7 meters per second, I wonder how fast that is. So you could actually do the reversal here if we want. We can take the 7 meters per second, multiply that by 1 kilometer, which is made up of 1,000 meters. Multiply that by the 3,600 seconds. The 3,600 seconds that are found in 1 hour. I apologize, that is a flaw in my programming there that made that jump. Okay, and let's see what happens. So here we're going to do 7 times 1 divided by 1,000 times 3,600 divided by 1, and we get the idea that I was going 25.2 kilometers per hour. So actually I was driving in a school zone and I was going under the speed limit, and my braking distance was still 3 meters on a nice day. You know, that's not that great. I mean, little kids could run out of those school zones pretty fast, and I'm not even going at the full speed in that zone, but I would still have trouble stopping if they ran out too close to my car. So that's one of the reasons to be cautious and not to, scoff at those school zones. I know that sometimes it can be frustrating when you're in a hurry that you're driving through those 30-kilometer-per-hour school zones, but really, your braking distance, even on a good day, is still going to be a fair amount, and we have not included our reaction time. So when we get down to the next section on the total stopping distance, we'll be adding in that reaction time and realizing that we actually have to think about a longer distance than just this 3 meters. I have to add in my reaction distance. All right, with that, we're done for today, and we'll talk to you in the next video. Have a great day.